In November 2019, Pedro Ribeiro and Radek Demansk of Flashback team traveled to Tokyo, Japan for ZDI's mobile pwn-to-own competition. With them, they brought a command injection vulnerability as a part of an exploit chain they used to gain code execution on a TP-Link Archer A7 wireless router. Take a look.
In their final attempt of the day, Pedro and Radek targeted the LAN interface of the TP-Link AC1750 smart Wi-Fi router. They used a total of 3 different bugs, starting with the command injection vulnerability, to get their code executed on the target. They earned themselves another $5,000 and half a master upon point.
In a YouTube video published January 6, 2021, Pedro and Radek explained their process for finding this command injection vulnerability. Although their technical explanations were extremely well done, it was what they didn't explain that intrigued me the most. Around 6 minutes into the video, Radek explains that they use a set of scripts to try to find vulnerable parts of functions. One of these was modeling a vulnerable system call. Check this out.
With Pedro, we have a bunch of automated scripts for vuln hunting. We used one that helps us to flag a potentially vulnerable parts of the functions. That way, we are able to quickly find a vulnerable system function call. So finding the vuln was easy, but don't be fooled. There was a serious reversing effort involved in order to understand how to deliver the payload to the target. And with this, I'm off to Pedro, who will explain that part.
So let's see what we can do to model vulnerable system calls using Ghidra.
All right, so let's go ahead and get started with analysis. What we're going to be doing is taking a look at the same firmware version that Flashback team were taking a look at when they were at Pondo in Tokyo. So in this particular one, it's a TP-Link Archer A7, MIPS version, hardware version 5, and then this version for the firmware version. I was able to find this online, download it, just open it with 7-zip, and extract the vulnerable binary, which is user bin TDP server. We have user bin TDP server analyzed in Ghidra. This is the most recent version, 9.2.1. And in here, we can see that this is MIPS. So in this location in the middle, I have my disassembly. On the location on the right, I have my decompiled output. On the location on the bottom right, I have my sort of like script manager here where I'll be running things from. The script that we're going to be taking a look at analyzing is the system call auditor that I wrote. This is basically just checking for those vulnerable command injection via system calls, at least one pattern of it. So when we run this, we'll notice the output comes out through here, and this is the script output that we'll be doing. There's sort of 3 discrete components to this. The very first one is checking to make sure that it makes sense to do any analysis on this binary. And that means just making sure that the presence of these 464 functions here relate to sources and sinks that we actually care about. So in our case, it's the sink system, which is sort of where data goes to cause a problem. For command injection, it could be system, it could be exec_ve, it could be popen. There's so many different things that could be viable sinks, but in our case, we're only looking for the vulnerable system call. We can add more to it if we'd like. For vulnerable sources, think of user inputs. So it could be something that reads from USB, something that reads from a socket like receive, something that reads from a file. In our particular case, what we're going to do is we are going to simplify the heck out of this problem. And we're going to say for command injections, typically what I see are some static data that exists in the binary, like I want to call IP tables and set up some type of routing information. That routing information is dynamic. We don't know it a priori. It's the user setting it up. So if they give us that information, we can take it and smash it together with information that we know is the right formatting for this command, and then we'll put it together with sprintf or snprintf, and then we'll give it to system. That's what we're modeling. So we're going to sort of lie or cheat here and say that the source of our data is snprintf or sprintf when it's really more complex than that. So once we have that, we want to go and make another assumption here. The assumption is that both our source and our sink are going to be called from the same function. This is not always the case, but it is an easier assumption or an easier way to develop this type of signature. We're sort of trying to lean on the 80-20 principle. So what we're trying to do is do 20% of the work and get about 80% of the output without having to really over-engineer things. If we lift this requirement here or this assumption, this gets so much more complex, right? So we're going to stick with this and just say that let's assume that our sources and sinks exist within the same function. In order to do this, what I need to do is go to each one of these functions and just make sure that they call at least one source and sink. Out of 464, there are only 3, right? So we had a lot of things to analyze, and now we have little to analyze. Now we'll go one step further and take a look at our sources and sinks and see if they're related by the same variable. If they're related by the same variable, then whatever is being formatted here and put into this location is the same thing that's being executed here. At this point, we can go ahead and alert and just say, yeah, it looks right. Just go ahead and take a look at it, verify that this is right. Turns out that this is wrong. This is a false positive. There was not a source and sink both called from within this function. And in this one ends up being a true positive. So this ends up being a command injection. And we'll take a look at how that sort of manifests and builds out, but let's go take a look at the actual script. So what I'm doing here is I'm going to be editing this inside of Sublime Text. If you go into, at least on Windows, your use directory Ghidra scripts, and you create a script inside of here. In this particular case, I've tagged it in the category of HackOvert. So it's going to show up in my script manager in the folder HackOvert here. So I can go ahead and just refresh this and run this whenever I need to. The built-in command editor is sort of like IDA's. It's not that great. It doesn't do syntax highlighting, and it's just easier to do it out here. All right, so the very first thing we need to do to consider is we're going to have a main function so we can return and bail out early. Nothing interesting about that. What we're going to do is we're going to utilize some pieces of the Java or the Ghidra API. First one is console task manager. That's just going to allow us to cancel scripts that are running that might be long running. For example, this thing that pops up here allows us to cancel it. That's what that console task monitor is going to allow us to do. var nodes and var node AST is abstract syntax tree, are going to be really important for us because they are the sort of building or basic blocks in which P-code, at least refined P-code, is built on top of. It's going to be really important that we're able to take a look at these guys here. And the way that we're going to get this is through a decompiler interface, which can take decompile options. All right, so we have our sources and sink and our one sink listed into Python lists here, or basically an array. And these are just the names of those functions, right? We're going to take a look at what these two sort of helper functions here are. Sort of in the third step, let's ignore those for now. In the main function, the way that we're going to do this is when you open up Ghidra, and I open up the Python editor here, if I were to do that, and I just type in current program, it'll give me the current program object. It says, here is the program that you're working with. Right now, that's loaded. So in that particular sense, I can say, get me a function manager from the current program. And again, this isn't defined anywhere in my script because it's defined by Ghidra. We'll get that function manager and we'll say, get me functions, right? So it's going to go through all 464 functions. True just means iterate forward instead of backwards. And for each one of those functions, just throw the function object into this list. So in this particular case, after functions, I'm going to go for functions in functions, and then we're going to put the name of it into a new function. So this is just going to be a list of strings. So I have my sources, right, up here, which are sprintf and snprintf, and then the function names that are in this. So the 464 functions that are in this. So all of these names get kind of thrown into a set. This gets thrown into a set, and then when we look at the basically the union of those sets, we're going to have left over snprintf and sprintf because they both exist in this binary. Same thing with this. We're going to have a resulting set that has one entry. So basically, if both of these things have at least one entry, we know that we have at least one source and one sink, and we can continue analysis. Otherwise, we just need to bail early. All right, so that's step one. Step two is to find functions that are going to call at least one source and sink. There are probably many different ways to do this. The way that I chose to do it is to create an empty list called interesting functions. We'll go through the function objects again. Again, this is not function names, it's function objects. I'll go ahead and kick off a console task manager, or instantiate a console task monitor, pass to get called functions. And then for each one of these guys, I'm going to go ahead and get the name. So we're going to get a list of all the called functions. And basically what that means is inside of this function, there's two call points, and that's going to call this function and then this function, right? So we'll basically just be getting these two strings, okay? And inside of those two, we're going to take a look at those callers, source and sync callers, and we're going to see if there's at least one in each one. Then we're going to append that function, the calling function or the caller, to this interesting list. And then we'll just make sure by count, if there are 0 or less than 0, which is not actually possible, we're going to just say, hey, like this, nothing was interesting that we found, so we're going to go ahead and bail early. Otherwise, we'll go ahead and keep this around and just kind of print out the functions that seem interesting. So that's what we've seen so far up to this point. If I'm going to rerun this, this is step 1 up here, this is step 2, and now we get into the good part, which is analyzing each one of these. So the very first thing we want to do is go to each one of these functions. We'll create sources and sync arguments, and we want to get a high function for this. This is something that we don't really need to break out to another helper function, but this is something that we'll probably use quite a bit, so it's nice to do it. Essentially, we get a function object. We're going to get instantiate a decompiler options. Now, I do use this in some of my other scripts, so there are lots of options that you can use that come out of this to set for sort of information that you might not need or simplify some of the output that comes out. But for this particular case, we're just going to leave everything default. We're going to create a decompiler interface or instantiate that in IFC. We'll set our options. We'll open this current program. Seems silly, it's already open. We'll basically just get a handle to it. And then we're going to decompile that function. We'll give it up to 60 seconds to do that. Otherwise, we'll fail. And then we'll return the high function object from that. So once we have a high function, we can then go through P-code operations. So P-code is the intermediate representation for Ghidra, right? Let's take a look at sort of the two forms of P-code. If I come in here and I turn on this row, so I enable this field, here's going to be the raw P-code. So when we take a look at an individual instruction, we can see that there are a few different things going on. There's an add, a couple copies, we're storing something. And even if you're not familiar with MIPS, you can sort of break down these individual components and learn a little bit about what that instruction does. And this is the same on any architecture. What's great about this is that we don't have to write an analyzer for MIPS and write an analyzer for PowerPC and write an analyzer for ARM. We could just do it on top of P-code and we don't have to worry about this. But this is not the P-code that we're going to be analyzing. Strange, huh? This is sort of a raw P-code representation. The actual P-code representation that we're going to be looking at is quite a bit different. And it actually relates almost one-to-one, essentially one-to-one, with the decompiler output over here. So keep in mind, this is what raw P-code looks like, and what I call refined P-code is over here. So I don't know what the actual name of that refined P-code is. If you look in documentation for Ghidra, you essentially see P-code represented as P-code. Sometimes they'll say raw P-code and then just P-code. So this doesn't seem to be really distinguishing between the two at all, but let's go ahead and see what this actually looks like. So I put a print in here, and this looks quite a bit different. So there's some stack references, registers, these concepts of uniques, which we won't go into. And this is it. I mean, so these are call operations. I have this sort of filtered out. So let's see, like this is what everything's going to look like. And these two or some of these things end up looking the same. It might be hard for me to find one right now, but they're very unique in the sense that the information that's printed out might be the same, but they have backing unique IDs and hashes, different information about like where they're actually located. In terms of physical or like a PC address. So there's a ton of stuff backed within these particular objects, and they look very much different from this because there's a lot of analysis going on between this stuff up here, this P-code, which is raw P-code, and all of this P-code down here. So we're going to go ahead and disable this because we don't actually care about it. And what we're going to do is we're going to only look for the things that we really care about in here. There's going to be a lot of different things that get spit out from here. Essentially what we can do to make sure we're looking at a call from this is when we take a look at a P-code op AST or abstract syntax tree, there's a method called get mnemonic. So let me go in here, and I think I already have it pulled up. So the best way to get sort of like information on this is to come in here and go to Ghidra API help. That'll pull up sort of a local version of this. And we can just search for P-code op AST, scroll up to the top. And this extends P-code op. So anything that's available in P-code op will be available in this particular object. That is going to be all of these methods and these methods here. And any fields will be listed up above too. So in this particular case, if we're looking for, I think what we did was get mnemonic, which is actually related to the P-code op. So if we click on get mnemonic, it'll tell us more information about that too. So this is really just going to give us, in this case, C branch or call. So that is what we're interested in. What I'm going to be looking for here in the next section is that we're going to be looking for calls, right? And the very first entry inside of that comes back is going to be the location that's called. So for right here, it's calling, there's a call being made here to this location, okay? So when I go and say, get me the inputs, and the op input at the first entry is going to be the call target, I can get the address for that, and then use my function manager and say, get the function at this address and give me the name of it. So then I get the name. So from here, I repeat myself. So this is not dry, right? It's not, do not repeat yourself here. I put all of these in discrete so that if you wanted to do separate analysis for each one of these things, you can. But it turns out it actually doesn't really matter for our case because we're really interested in that first argument to each one of these functions, then making sure that they're tied together. So right here, the mnemonic is call. We'll go ahead and get the name of it. If it's system, we'll do something. If it's sprintf, we'll do something. If it's snprintf, we'll do something. If it's something else, then we just won't do anything. Okay, so let's go ahead and take a look at what these call mnemonics sort of look like. So when we have an operation, a P-code op, that is a call, what those end up looking like. And this is what we're trying to analyze to get information about the first parameter of them. So all of these are call operations, obviously. This will be pointing here, which is stir and copy. Turns out this one's going to be calling system. So the very first entry is going to be the location that we're actually calling. So when I do this, we're actually getting the call target. We could do get address from that. And then we can use our function manager that we already have, call get function at that address, and then do get name to get a name. What we then do is then compare these, right? So another thing that we need to do is when we figure out a function that we want to analyze more, like system, sprintf, snprintf, is we need to get that first parameter to it. In this particular case, from the call function, we get the location that we're calling, and we resolve that to system, and then we want the first parameter to system. If we do that, what we're going to end up getting are these unique values or things like registers. If you look at these and if you kind of interrogate these objects, they won't really relate back to anything up here, which becomes extremely confusing because it's how do we actually know, or how does the decompiler even know that information that's coming out of here, or like a register, for example, with this calling convention, how do you relate that to stack information? Obviously, it does it inside of the decompiler. Well, what I've had to do is create sort of like a roundabout way to do this, and I haven't been able to find anything in the Ghidra API that allows you to do this easily. So what I call it is get stack var from var node. So basically everything that we're going to be analyzing here are going to be var nodes or var node AST. What we're going to do is give it the function object that we're currently analyzing and this argument, which is going to be the first thing that we want to know about, okay? What I'll do is go ahead and take a look at this thing here that we're doing. The very first thing is we need this var node to be a var node or var node AST, which we imported up here. If they're not, this is not going to work at all. So we just do kind of a sanity check. We don't check function to make sure that it's a actual function type, which is kind of funny, but at any rate, so we do function and we can do get all variables. What this is going to do is sort of give us like just the generic variables. So for example, these locals here that occur in this function, these are going to be the things that come back. But when you see things like AC stack and AU stack, none of this stuff is going to be there in that, right? So what we're going to do is we're going to do the first pass to see if any of those locals match what we're looking for. And then we'll try something a little bit different after that point, which is going to be getting a high function and getting a local symbol map, which is different than the variables, right? We're going to get everything in terms of all the symbols that are inside of that function, and we're going to try to do correlation there. So from getting this, what we're going to do is get all variables, right? Get the var node, and I'm going to say get the definition point. Like, give me the first point where this thing is actually declared inside of that function. And if that actually exists, which we really need in order to do any analysis, I'm going to say give me all of the inputs to that. And then for each one of those inputs, we're going to go through and see if they correlate to anything within those local variables, right? So that first definition is going to have points that will be like an offset from the stack pointer or the base pointer or whatever, right? So like that concept of getting that offset is going to be really important to doing this correlation. If this works, we'll just return it. In our cases, it's not going to work at all. So we need to get things like the AU stack or AC stack. And the way to do that is through the get local symbol map. So I'll give it this function. We'll get the high function. We looked at this before. Just gives us a high function from the decompiler. From that, we'll get this local symbol map, and we'll basically do the same thing. I don't want parameters, though. So in certain functions like this one, these parameters will come back in the symbol map. I know that like those are things that I don't want because I want to be correlating to this. It's possible that we could have a function that's called like param1, and then param1 is passed directly into system. But again, we talked about earlier that we wanted to make this as simple as possible, so we're not kind of even considering that case, right? So we're just going to just ignore any parameters. And then there's this concept of get storage, which is like, where does this relate to on the stack? Getting this var node and then the offset. From this information, if these two are equal, then we'll go ahead and return that symbol. It's going to be a map symbol type. So from map symbol, we can come back up here, search for that, and we'll get information about like what the heck that actually is. A lot of this was really kind of trial and error to try to understand how this stuff works and how it relates. This was a giant headache to figure this out, and I really wish, and it probably does exist, but I really wish that the Ghidra API just had nice ways to correlate var nodes to like stack variables and stuff, but you have to do this sort of roundabout thing. But the API is so massive that maybe it does exist and I just don't know of it. So at any rate, once you do this sort of magic function, we'll call it, because there's a lot of work put into figuring that out. From the stack variable, we're going to go ahead and take a look at the target address, so the address. Basically, we're looking at where is that system call made, so we can print it out nice and easy, and we can just double click on it and it'll bring us directly to that location. We're going to keep track of that interesting sync, and we're going to get the name of it. So in here, when I ran this, hopefully I removed that. No, I didn't. Go back to this and remove this. One of the interesting things that we saw was that we're able to recover this variable name now. So the system command, if I go here, I renamed that. I'm going to go ahead and keep track of that. And then after all of this analysis is done, I'm going to go and do the set operation thing again. We essentially look at the union of these sets, and we're saying, tell me when, let me know if there are any matches here. That means that our source, whatever one we found, whether it was sprintf or snprintf, and our sync are utilizing the same argument as the first for the first argument. They're utilizing the same argument. So what that means at that particular point is that there's some value that gets kind of formatted together and then passed to system. At this point, we can do so much more work and analysis. We can take a look at data flow and control flow to verify that the snprintf or sprintf actually occurs before the system in the actual like control flow logic. There's other things that we can do by actually analyzing the format string itself and looking at the specifiers and then relating that to other parameters that being passed. Let me show you what that would look like. So when I run this, this very first one is a false positive, and the reason why it's a false positive is because we don't do verification, any further verification on what this means, right? So in this case, we have our actual command, which is an echo command. the %s is this guy, which we cannot inject to. It's static. And then the %d, it's a variable it seems like we might be able to inject into it, but if you look up, there's all just like static defined points where this takes a value. And even if it was something I can injecting into an integer just isn't very interesting at all. We really want to execute some type of command, which generally requires a %s format specifier, and that's basically out of the running here. So if I were to extend this script a little bit more, what I would do is verify that this occurs, and if that occurs, as a step 4, go back to these sources, take a look at this command, parse out the format specifiers, so like all of the %s's, the %d's, the %c's, the %p's, whatever else it is, and then go after that, say if we found 2, go to the next arguments and see if they are variables or if they are just static strings, right? And then from there, we can go and take a look at the possible values, where they occur and what they take on, and do more and more and more analysis at that point. If I were to look at something like this, like a system command, and find out that it's only concatenating, like there's no %s in here at all, then I would just bail and not even look at that case anymore. If there was a %s, I would take a look further and further and further, and you try to give yourself these early exit points to not continue doing analysis when you don't need to. In this particular case, this ended up being vulnerable, and the reason why is because there's a direct connection between, let's see here, this variable and this variable, but this is really the key point. And our analyzer doesn't actually find that information out. But this is where you as a human would take over and start doing that analysis to try to find this in the first point. So what we want to do is throw everything in the hopper, run the script against a ton of binaries, and hope to find these interesting, what we call points of interest. And we can go take a look at these points of interest and see like, oh, hey, you know what, this does actually lead, like we can get user control data down into this point, and then kind of continue the exploitation process from there. So that is pretty much it. Hope the concept of all of this makes sense, and I kind of went through it a little bit fast, stumbled along the way, but if you have any questions or comments, feel free to let me know.
So there you have it, a script that can help you triage targets to take a look for vulnerable system calls. At this point, there's so much we can add to this particular analyzer to help us in terms of control flow, to make sure that there's no sanitization in between. And again, just like Flashback team suggested or talked about in their video, there's so much work that still needs to be done after finding this potentially vulnerable pattern. You have to trace that data flow all the way back up into something that might be taintable by the user or an external attacker. This is something that is really, really difficult to do, even with the best tools that we have available today. But it's something that is a bit of a start, and it's only a couple hundred lines of code.